Well, today's topic is energy. First, we're going to define what energy is, and then we're going to talk about energy as a very powerful problem-solving tool by sort of organizing energy into a couple of different ways of looking at it. First of all, here's what energy is. It's not a thing. Energy is a potential. It's an ability to do one of two things. Work, and we've defined work already as moving an object with a force through some distance, or causing a change in temperature. We're going to focus on mechanical energy in this little segment here. So we're not looking at the change in temperature thing. We're going to leave that for a later unit. We're going to focus on the interchange between stored ability and doing work. In systems, energy can be stored in two different ways. One of the ways that you can store energy is in the positions of objects that are in the system. If you have two objects that for some reason are attracted to each other, like let's say two magnets. Here's a magnet with a north pole here and a south pole here, and another magnet over here with the south pole here and the north pole here. There's an attraction between these two objects, and if you hold them apart from each other, you have stored energy in that system of magnets. Another way that energy can be stored in position, we can also illustrate with magnets. Let's say that I have two magnets that are lined up north pole to north pole, like this. Well, the magnets don't want to be close to each other. If you've ever tried this with magnets, you know that. And so they repel each other. If I hold them close together, I store energy in the system. The ability to do work is stored in the positions of objects. There's a lot of different ways that this shows up, but it always comes down to objects that attract being held apart or objects that repel each other being pushed together. All of these kinds of energy are called potential energy by physicists often. It's a little bit of a misnomer because there really is only one kind of energy, but this is just a shorthand way of describing energy that is stored in the positions of objects. PE, or that's short for potential energy. We're going to look at a couple kinds of that. And another way that you can store energy is in the motion of objects. If I have an object that's moving, like say I have a baseball and I have that thing moving, it's at some speed. Well, that moving object has the ability to do work. If it smashes into a wall or hits me in the eye or something like that, it's going to do work. And so it's storing the ability to do work in its motion. We're going to take a more detailed look at energy of position from two standpoints, two kinds of energy of position that are important in physics, and then we're going to look at kinetic energy a little bit later. The energy that's stored in the position of an object, no matter how that is done, turns out to be equal to the amount of work it took to get it to that position. So potential energy is work. They're going to have the same units. The amount of work it takes to get that object in position is the amount of energy that's stored in its position, and when that energy is released, it can do exactly that amount of work. One way that we can store energy is in the positions of objects. This is one type of potential energy. Like, let's take an example of yourself. You're attracted to the center of the earth, so there's an attraction between you two. And then here's a stepladder. Let's draw up there, a stepladder. And if you were to climb up the stepladder and stand on top of the stepladder, it took work to do that, to get up there. You notice that you have changed the energy stored in the system of you and the earth. You're still attracted to the earth, but you've been moved away from its center. Well, the potential energy that's stored, we're going to call this gravitational potential energy, is just equal to the work that it takes to get there. But work is equal to F times delta D. So F, that's your weight, mg, and delta D, well, that's just the height of the stepladder that you climbed up. So in general, we can say that gravitational potential energy is equal to the mass of the object times g times the height that object has been elevated. Here's an example problem. We have a 95 kilogram boulder perched at the top of a 300-meter cliff. How much energy is stored in its position? Well, since this thing weighs or has a mass of 95 kilograms, and since potential energy, gravitational potential energy, is equal to mgh, we can easily quantify this. Mass 95 kilograms, g 9.80 meters per square second, and the height here is 300 meters. Well, this is a lot of energy. Numerically, this turns out to be 279,000. If you look at the units, you can verify that this is energy because it's kilogram meters per second squared times meters. Well, that's Newton meters. or joules. Another way energy can be stored in positions of objects is if the objects are on the end of a spring. Now, earlier we learned that the work done in stretching a spring is equal to 1/2 k times delta x squared. So no surprise then, since work equals potential energy, the elastic potential energy is 1/2 k times delta x squared. Same equation. So you can figure out how much energy is stored in a spring if you know how much it got stretched. Let's look at this example problem. We have a clicky pen. We know how much energy it's stored, so that's our PE elastic. We know delta x. We know how much it got compressed. So stretching and compressing, same thing it turns out. That's our delta x. And what we want to know is what's the spring constant? What is K? Well, we know that potential energy elastic is equal to 1/2 K delta x squared. So that means 2 times potential energy is going to be K delta x squared. So that means K will be 2 times potential energy divided by delta x squared. So 2 times our energy of 0.0225 joules over 1.0 centimeters. Oh, let's change this to meters. So that'd be 0.010 meters squared. This is going to give us joules per meter, energy per unit length, and that's a good unit of K. If you calculate this out, you find out that 450 joules per meter are stored. Well, we've got another rotational analogy. The elastic potential energy of a linear spring is 1/2 K delta x squared, but for a torsional spring, for one like on a mousetrap or in a clock that you wind up the spring, there's a similar equation, an analogous equation. PE elastic for a torsional spring. These are called torsional springs because torque goes on them. Torsional. That's going to be equal to, not K, but a Greek letter called kappa, looks just like a K almost, times delta, not X, but theta, because that's our analogy for displacement, divided by 2. Well, here's an example using that. Here we have to find the torsional coefficient. We know how much energy is stored, and we know here's delta theta. It's 180 degrees. So PE is 1/2 kappa times delta theta squared. So that means 2 times PE divided by delta theta squared would be equal to kappa, our torsional spring coefficient. So 2 times 2.75 joules divided by 180 degrees quantity squared is going to give us units of joules of energy per degree stored. If you do the arithmetic here, you come up with 1.70 times 10 to the negative 4th joules per degree. Quite often, coefficients of torsional springs are not in joules per degree, but they'll be in joules per radian, which is really just joules because radians are unitless. So if you see that, you'll know what you're seeing. Well, we have a law called the law of conservation of energy. This is also named the first law of thermodynamics. It's an alternative name for this thing. And it's one of the most important laws in all of physics, and all of the physical sciences, in fact. And that is that energy is conserved. And we're going to simplify that, kind of take a subset of this law, and say that mechanical energy is conserved in changes that involve no dissipative factors. So here's what this means. If there's no friction, the total amount of mechanical energy, total amount of energy in the system, is conserved throughout a change. So we could say that the sum of all the energy initially, before the change, is equal to the sum of all the energy finally, in other words, after the change. And since we know energy can be stored in 2 methods, we have to think about summing up all of the potential energies that the system initially has and all the kinetic energies that the system initially has. And that's going to have to be equal to the sum of all the final potential energies and the sum of all the final kinetic energies. Well, we can use this, it turns out, as a very powerful problem-solving tool that makes solving problems about motion much easier than they otherwise would be, and it also makes some problems that are nearly unsolvable or unsolvable possible to do. Here's an example of a problem that we can solve using the law of conservation of energy. A clicky pen spring stores some energy. It's compressed by 1 centimeter. This is the same clicky spring we had before, clicky pen. If the pen has a mass of 15 grams, what will be its maximum height if launched by this spring? We could do this using the stuff that we already know about motion, but it would be way harder than what I'm about to do. So here's our clicky pen situation. We have the clicky pen. It's got some energy stored in there, some potential energy elastic, and it's on the ground. It's going to jump up to some height, and then, of course, it will come down. When it reaches this height, it will have a potential energy that's equal to mg times whatever the height is. Down here, it's not moving yet, so its kinetic energy is nothing. Up here, when it comes right up to the stop at the top, its highest height, before it starts to come back down, its kinetic energy is again 0. So if we take the law of conservation of energy that says the sum of the initial potential energies and the initial kinetic energies has to be equal to the sum of the final potential energies and the final kinetic energies, we find that that Ke and that Ke are really 0. So that means that the initial potential energy, and there's only one, so I'm not going to do the sum sign, has to be equal to the final potential energy. And the problem tells me that my initial PE here was equal to 0.0225 joules. My final potential energy, well, it's gravitational potential energy, and that's just mgh. So if I want to know how high this is, it's just 0.0225 joules divided by m times g. 0.0225 joules divided by the mass of the spring, well, it was 15 grams, that's 0.0150 kilograms, and g is 9.80 meters per second squared. A joule is a kilogram meter per second squared times a meter, so this will just end up being meters because the Newton part will cancel out. Numerically, you get 0.1